So let's study finite fields. And what I'd like to do is I'd like to do a generalization of this example here, or not really a generalization, but a twist on it. First of all, notation. GF16 is standard notation for a finite field of order 16. GF. What? G is in honor of Galois. Galois field of order 16. But wait a minute, 16 is not prime. How can there be fields of orders that are not prime? Aren't ZP all the fields that there are where P is prime? No, we've seen examples of fields that are not of prime order. Like I think we've talked about a field of order 9 and a field of order 27, maybe. 20, I think 25 and 27 are examples we talked about in class. 16 is not prime, but it is a prime power, right? It's 2 to the 4th. And that is something that needs to be true about the finite field, is it's got to have an order equal to a prime power. Being a prime power where the power is bigger than 1, 16 is not prime. It's not going to be isomorphic to Z something. It's not isomorphic to Z2 because it's bigger than Z2. It's not isomorphic to Z16 because Z16 is not even a field, right? 16 is not prime. We know Zn is only a field when n is prime. Z16 is a ring, but it's not a field. It's not even an integral domain, right? There are zero divisors. 4, for example, is a zero divisor. 4 squared is 0. But there is a field of order 16, and we call it GF16, Galois field of order 16, though the way it's represented could be different. Technically, you could call them different fields, but they're isomorphic, so we don't. Here's, in this example, this is one way to construct GF16. This polynomial, x to the 4th plus x plus 1 is irreducible over Z2. Why? Well, it doesn't have any roots in Z2 for one thing. You'd also have to verify it doesn't have any quadratic factors, right? By the way, this came up on the last exam. I think we talked about an example where we had our polynomial was degree 4, degree 5. And in the example, we talked about how the fact that it didn't have any roots meant if it was degree 4, it didn't have any roots, so it didn't have any linear or cubic factors, but it could have quadratic factors. If your polynomial is cubic to start with, you only have to verify it has no roots. You don't have to say, oh, it doesn't have any quadratic factors, because if it's cubic and it doesn't have any linear factors, then it's not going to have any quadratic factors. So we'd have to verify this has no quadratic factors. But it must not. Actually, this is making me realize my example that I was thinking of may not work, although another example may. Anyway, since it's irreducible and it's got degree 4, we know from a theorem that all the elements of this field could be represented in this way. For any 0a of this polynomial in GF16, which is evidently a field extension of Z2 that contains a 0. Does it? Yes, that's a claim the author's not proving here. You're going to be able to write this. Why? Again, because it's irreducible. It's got degree 4. So the degree of the extension is 4. The elements 1, a squared, and a cubed will be a basis for this thing as a vector space over Z2. And as a vector space over Z2 means these coefficients are in Z2. And there's a typo here. There should not be a C4 there. Lots of typos in this edition is something else. If you notice something that seems like a typo, it may be a typo. That's a typo. There should be no C4 there. All right. And what the rest of this example is about is doing some arithmetic in this field. How to multiply and how to add elements. Let's do a similar example. Let's construct GF16 in a different way. How? I'm just going to change that x to an x cubed. I was thinking initially changing it maybe to an x squared, but I think that won't work because I think if it's an x squared, it becomes reducible. I think. I'm guessing. Not sure. If I square this thing, I multiply it by itself, what do I get? Well, maybe not. I do need to mod the coefficients by 2. I get that. So that's illustrating, this is what I'm illustrating here with this calculation is this thing is reducible over Z2 because it factors. It's got quadratic factors. It also has 1 as a 0. What if I multiply this thing by itself? What would I get? X to the 4th. I'm going to multiply this x squared by each term there. Then multiply the x times each term. Then multiply the 1 times each term. Stacking them like this, and then simplifying, reducing coefficients mod 2. Okay, yes, this is illustrating I cannot use an x squared in the middle. This polynomial, even though it has no zeros in Z2, is reducible over Z2 because I can factor it like that. Product two quadratics, which are both irreducible because they have no zeros in their quadratics. So if I'm going to hope to make an example that works, I think I have to make an x cubed instead of an x squared. Yep, for sure I can't use an x squared. I believe f of x equals x to the 4th plus x cubed plus 1 is irreducible over Z2. Kind of trusting it is by symmetry with the odd power there sort of matching in the book's example, the odd power here. And, you know, kind of by symmetry of imagining factoring these things as product of quadratics, you would think if this has two quadratic factors that this would as well, and vice versa. If this one doesn't, then this one probably doesn't. I'm not going to prove that. I'm just going to take it on faith. I might be writing something wrong. That this is irreducible over Z2. I feel pretty confident that it is. Definitely has no linear or cubic factors because it's got no zeros. I think it doesn't have any quadratic factors. Certainly, when you square these things, you don't get that. I mean, if I multiplied one of them by the other, would I possibly get this? I suppose that's worth checking. I multiply that, I get x to the 4th plus x cubed plus x squared plus now 1 times everything x squared plus x plus 1. Yeah, that the x squared's coefficients cancel mod 2, but the cubic and linear terms are still there, not giving us this. Guess I'd also want to check multiplying by x squared plus x, but that wouldn't work because that's got a 0 in Z2. Yeah, in fact, that's another quick way to think about these things is x squared plus x and x squared plus 1 both have zeros in Z2. 0 and 1 are zeros of this one, and 1 is a 0 of that one. So because of that, they couldn't possibly be factors of this because it doesn't have any zeros. Okay, so what can I say based on this? Yes, I could write a factor ring. That would be a field extension of Z2 with 16 elements and contain a 0 of this, x plus the coset, or x plus the ideal, that coset. But again, the theme of chapter 21 is we're trying to avoid writing cosets. We're trying to avoid having to think about factor rings. So effectively, what we do is we think of the GF16 that we're going to construct in terms of that theorem, we just write if A, where A is not the word A, right? Not the indefinite article, but an element. If A is a 0 of f of x in some extension field E of Z2, and we know f of x will have a root in some extension field because of Kroneker's theorem, then we can represent GF16 in a similar way as the book's example. Say C3a cubed plus C2a squared plus C1a plus C0, where all these C's, let me not make the same typo as the book does, are from Z2, so there are 16 elements in there. 2 to the 4th, you've got 2 choices for each of those C's. They're all zeros or 1. And this means you can write the elements of GF16 in this way as linear combinations of these powers of A. So I'm going to go ahead and write them all out. There'd be 1, there'd be A, there'd be A squared, there'd be A cubed, there'd be 1 plus A. You know, here you're writing them high degree to low degree, but here I'm writing them low degree to high degree. Oh, well, doesn't matter. 1 plus A squared, 1 plus A cubed, A plus A squared, A plus A cubed, A squared plus A cubed. So I've got all the terms so far with either, all the elements with either 1 term or 2 terms, right? Haven't missed any. What about with 3 terms? There would be 1 plus A squared. There'd be 1 plus A cubed. 1 plus A squared plus A cubed. Just 2 more elements. A plus A squared plus A cubed. And then finally 1 plus A squared plus A cubed. I miss any? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Oh, I must have missed something. Oh, I missed something very simple. Well, the ones there, 0. That's what I missed. That is GF16. When A is a 0 of f of x in some extension field of Z2, I'm not saying what the extension field is. Actually, A could be a coset. I'm just not writing it like a coset. A could be, you know, in fact, that's in reality what A probably is. A could be x plus the principal ideal generated by x to the 4th plus x cubed plus 1. That could be what A is. But it's so time saving not to bother writing it as a coset all the time. Writing elements in here as linear combinations like this makes it really easy to add them. For example, 1 plus A squared plus A squared plus A cubed. Just add them like they're polynomials. And yes, you should mod the coefficients by 2. This field does have characteristic 2 as a field extension of Z2. That's how you do addition there. But multiplication is not so clear. Go ahead and multiply these. I'll FOIL this out. A squared plus A cubed plus A to the 4th plus A to the 5th yes, that's true. That is the product, but which of these 16 elements is that? Here's where you got to use the polynomial. And the fact that A is a zero of the polynomial, this particular polynomial, we know f of A is 0. So a to the fourth plus a cubed plus 1 is 0. So a to the fourth equals negative a cubed minus 1. And yes, we are modding coefficients by 2 here in this example. That's the same as a cubed plus 1. And that is now makes it start to feel similar to the examples we did with factor rings. We just don't have to bother with the ideal. We don't have to represent these things as cosets, even though they may literally be cosets. We can replace a to the fourth with a cubed plus 1. We can therefore replace a to the fifth with a to the fourth plus a, where we also want to replace a to the fourth with a cubed plus 1. I guess now I'm writing from highest power to lowest power. Doesn't matter. Ultimately, a to the fifth gets replaced by a cubed plus a plus 1. So therefore, 1 plus a squared times a squared plus a cubed is a squared plus a cubed. Replace a to the fourth with a cubed plus 1. Replace a to the fifth with a cubed plus a plus 1. Now combine like terms and mod coefficients by 2. Looks like we get a cubed, because there's 3 a cubes. A squared is only one of those. There's only one a, but there's 2 1s. So 1 plus 1 is 0. So if I've not made a mistake, and I very well could have made a mistake, hopefully not, that's the answer. But realize, even though we got this answer in this field, that the calculation would have had different details if you were doing the books example. Why? Because the book used a different polynomial to start with. So with the books example, a to the fourth gets replaced by a plus 1, not a cubed plus 1. Okay, but the theme is the same. And there's a theorem in chapter 121 that I hope you would agree sounds like it should be a theorem, is that GFPN, no matter how it's constructed, is unique up to isomorphism. Our field, our representation of GF16 here, though it is technically different than the books, especially with regard to multiplication, is isomorphic to the books example. The addition would work the same because there's nothing you have to deal with the polynomial when you add things, but the multiplication would be different, but be equivalent. With the addition structure, think about adding any element to itself here. You would get 0, wouldn't you? Because you're always modding coefficients by 2. Take any one of these elements, say this one, add it to itself. You're going to mod all the coefficients by 2. You're going to get 0. And that's going to be true for any element. All the non-zero elements of here have additive order equal to 2. And remember, fields are groups under addition. They're abelian groups under addition. an abelian group of order 16 under addition, what's this got to be isomorphic to under addition if you ignore the multiplication? Z16? All the elements as group elements, all the non-zero elements have order 2. As a group under addition, mod 2, GF16 cannot be cyclic. It's got to be isomorphic to the external direct product of 4 copies of Z2. That's pretty clear, actually, when you think about it. Again, all the non-zero elements have to have additive order 2. For a group of order 16, an abelian group of order 16, the only way the non-zero elements all have additive order 2 is if it's isomorphic to that. What about as a group under multiplication, or is that a faulty statement that I just made? Could it be a group under multiplication? This cannot be a group under multiplication because you got that troublesome element 0. Okay, take 0 away. Any field is not a group under multiplication until you take 0 out. Throw it away, put it in the trash. No, 0 should not go in the trash. Take it out, consider the corresponding set of non-zero elements under multiplication. That does become a group. And with finite fields, that group is, it turns out, cyclic. It's not obvious. But if you get rid of 0 here, the resulting group of order 15, right? 15, we took out 0, is cyclic of order 15. It's isomorphic to Z15 as a group under multiplication. It's cyclic. What's a generator? We'll come to that. Before we do that, I think it'd be good to find. So A is A0 of f of x in this field extension E of Z2, or in some field extension E of Z2. Am I saying E is GF16? Well, it could be. But maybe there's something smaller. That's another field extension containing A. Could there be like a subfield of this that contains A that's smaller? That could be. But does this have any other zeros in GF16 set? This is the point where I really got stuck on my written prelims in grad school. Like, how do I find another 0? This is the point where Nathan Gossett's dad, Eric Gossett, helped me most. Like, well, why don't you just do some synthetic division? Like, what? I can do synthetic division? A is a 0 of x to the 4th plus x cubed plus 1. So I could either try dividing x to the 4th plus x cubed plus 1 by x minus a, do some long division. That's more fun to do synthetic division, though. Quicker. Careful. Got to put all the coefficients there. There's the 4th degree coefficient. There's the 3rd degree. 0 and 0 are the 2nd degree and 1st degree. 1 is the constant term. Wait a minute. How do I do the synthetic division? Well, remember, A is a 0 of f of x. So you got to get 0 in the end. How's that going to happen? What is a exactly anyway? Well, don't worry about it, just do it. Okay, bring the 1 down. A times 1 is a. Add. Should give myself more room. Multiply. Add. Hopefully you gave yourself a little bit more room. Multiply. Where's this going? Add. Multiply. Add. Wait, did we accomplish anything? Hey, that's 0. Why? Because a is a root of f of x, and this is f of a. But wait a minute, what is a? Well, a is a 0 of f of x in some extension field of z2, which we know will exist by Kroneker's theorem. If you want to be more specific about it, yes, we could take that extension field to be, we could take it to be a factor ring. We could take it to be this thing. And we could take a to be the coset. That, if you want to be specific, we could do that, but we don't have to. Oh, that makes it more fun. We don't have to. And what does all this mean? It means we can factor the original polynomial x to the 4th plus x cubed plus 1. Yes, I will write it as x minus a, though since the characteristic here is 2, that's the same as x plus 2, plus a. X plus a mod 2. And these are the coefficients of a cubic. That helps us factor this. What is a? A is not necessarily 0 or 1, right? In fact, it's not 0 or 1. And if it was that specific factor ring, it's a coset. And so this is kind of weird. You can't mod those coefficients by 2. Because we don't know what a is. So what do you do with this? If we were trying to continue finding more factors, more zeros of f of x, we'd have to continue trying to see if any of these other elements make that 0. They might. They should, in fact. How many other elements? Probably three other elements. Probably we're going to be able to factor this as the product of 4 linear factors, probably with 4 distinct zeros, probably. So there's probably 3 other elements in this list. Not 0, not 1. We already considered a. So we only have 13 others to consider. 3 of those 13 are going to be roots of this. Which ones are they? That's tough to say without just trial and error. And I think I don't want to take the time for a bunch of trial and error. Well, let's just try one of them, seeing if it possibly works. And the author does this kind of thing in the textbook. Is a squared possibly a root? Well, okay, I could use this factorization here to technically evaluate this at a squared, though as far as figuring out if it's a root, I would only need to consider the cubic part. Most likely, since I'm using a different example, this may not work, but let's just see what happens. Again, that's not 0, so I won't bother simplifying that part. What's this part? A squared cubed is a to the 6th. A squared squared is a to the 4th times that is going to be a to the 4th plus a to the 5th. Here I've got a squared times that, so that's a cubed plus a to the 4th. For emphasis, this is going here to this part here. This is going to this part here. And then I've got a squared plus a cubed. Now that I've written the elements in this way, I can mod the coefficients by 2. So effectively, this a cubed cancels with this a cubed. This a to the 4th cancels with that a to the 4th. And writing equal there is probably bad. What I just did, but this entire thing over here is becoming this entire thing over here. So we're left with a to the 6th plus a to the 5th plus a squared. Okay, let's use what we found on the other page. A to the 5th can be replaced by a cubed plus a plus 1. What can a to the 6th be replaced by? A to the 5th gets replaced by a cubed plus a plus 1. A to the 6th can be replaced by a to the 4th plus a squared plus a. Right? All I did there was I just thought of a to the 6th as a times a to the 5th. Continuing canceling, for example, that a squared with that a squared, this a with that a, because we're modding coefficients by 2. And now replacing this a to the 4th with a cubed plus 1 from the previous page. We're almost done. Oh, amazingly, it looks like it's working. That's 0. Done. A squared is a root. Actually, I could have checked all this with synthetic division as well, but I would have still had to have done the same kind of calculations to reduce the powers. The author does say at the beginning of the chapter that finite fields are also fun. That's another way to do finite fields, another reason to do it. This is supposed to be fun. And it is once you kind of get used to it, right? I don't know what a is, but I know it's a root of f, so I can do these calculations. Okay, again, I really do know what a could be. It could be that. That was what was most confusing to me. My written prelim questions could be figured out often by doing this kind of thing. I remember some of these kinds of questions, factor f of x completely in some extension field of Z2 are like, what? How do I do that? This is the start of it. This is like one of the PhD written prelim questions right there. But we've just essentially started. There are more theorems about finite fields as well that you should read about. And in particular, an important one that I quite often put in the final exam related to this tower of fields, or field lattice if you prefer, showing how subfield lattice, showing how GF 2 to the 24th power is structured in terms of subfields. 2 to the 24th is a humongous number, right? But there's only a fairly small number of subfields. It's this theorem here. I'll let you read and think about it. It's a little confusing, but once you start thinking about it and thinking about examples like this, it's not too bad. It's a little surprising that such a humongous field could have so few subfields, you might say, but that is the truth.